everyone, and welcome back to Activity 15. We are on the last part of this activity, and that's starting on page 208. And we're going back to talking about, again, our periodic functions. So a reminder when we were talking about Stacy and her bike with that diameter length or diameter of 24-inch sized wheel. And reminder that wheel went around every 4 seconds. So if Stacy's pedaling at 12 seconds, we know that when she's pedaling 12 seconds, that's going to be the same height off the ground as it was when she was pedaling at 4 seconds, at 4 seconds or 0 seconds, because she's just going around on this three full times to be 12, right? So it's that same idea as the original periods there. Same kind of idea with 14 seconds, right? It's actually going to be the same as when she was at 2 seconds, because officially all that's happening is she was able to go around the 3 full revolutions plus 2, though, right? So it's that same idea of that she's back to where she kind of began at 2 seconds or 6 seconds for that matter. So at 19 seconds, she's been able to actually make it around 4 full times, which means that it's the same as f of 3, because again, it's like going back to saying, okay, she made it around 4 full times plus 3 seconds, right? So it's the same idea as whatever it was at f of 16, or again, back at f of 3. They're all going to kind of have that same variation because of that periodic nature. Now, to 8 2/3 seconds, that means she's made it around 2 full times plus 2/3 of a second. So whatever it was at 2/3 of a second is the same value at 8 2/3 of a second, right? It's the same values there because of that periodic nature. And then all the way until we get to 49 1/3 seconds. Well, she went around, if she goes around 4 seconds, she went around 12 full times. But then she also went 1 1/3 second beyond that, those full revolutions. So really, it's again the same as it was at 1 1/3 seconds would be her height of that paint splatter off the ground. So we've got periodic nature of things just moving around, okay? Now, looking then back at this problem, if we go back to that idea that here's the paint splatter, and this is actually going to be time 0. And then when it moves up here, after 1 second, it's at 12 inches. Back down to 0. And then at 3 seconds, we are at -12 if we're considering this back to 0. Okay, think about this like the axis, right? So what's happening is at time 0, she's here. 1 second, she's 12. 2 seconds, she's back to 0. 3 seconds, -12. 4 seconds, back to 0. So we see this revolution, and we know because of that periodic nature of her pedaling, the graph would repeat itself, okay? If we look at this graph, and in part 3 here, it asks us to change this so that instead of being in the terms of inches, we say this is in terms of feet. What would happen is 12 inches would turn into 1 foot or -1 foot, and then this would just be half of a foot, -half a foot or +half a foot, right, if we go here. Officially, though, the graph would not be any different than it was before. Than it was before, being 1 foot down. All we did was call it feet instead of inches. So our graph would look the same other than that. Now, if we keep going then with that idea that we're going to keep this in feet and we're going to keep this, we're now going to change this instead of talking about seconds, we're going to talk about how much we move in degrees. Well, over that course of 8 seconds, we rotate around our circle 1 time, so 360 degrees, and then a second time, so 720 degrees. So what's happening with our graph is we see 2 full revolutions in these degrees, which means it would look like this, where we were up, down, back to the beginning by 360, same thing here. Oops, last part was a little off. So we're here, and then same thing here, we gotta repeat there as well. Okay. Now, if we were changing this, however, to radians, again, same graph, same scale, we're going to keep these the feet. But this time, instead of being 180 degrees, we know that it's pi radians, and 360 would be 2 pi, 540 is 3 pi, and then 720 is 4 pi. So again, this portion of it did not change, but instead what we see is just a different labeling of our scale since we are now in radian. Okay. Basically what is happening here is if we now graphed sine of x and we used this scale back here where we are starting at 0 and we're doing degrees, 720, and we're going up by 180 each time, and we're going from -1 to +1, going up by 0.5 each time. Because our calculator should be in degrees mode, what we're going to see here is that our graph looks identical to what we had in part 4. Okay? And what would happen here is if we change this to radian mode, we would then have to change the window to be 0 to 2 pi, going up by pi's each time, and we would see that we would get that same graph as what we now have in number 5, okay? The reason being, this is basically the parent function of our sine graph. And if you look on page 210, that's what they're getting at on page 210, is looking at that and seeing that this is the same. Now also on page 210, you see again the trigonomic definition of sine, and talking about what we were talking about with activity 14 of the sine being the opposite sine over the hypotenuse. Now in this case, in the case of the unit circle or art circle in general, the opposite side is always the y value, and then the radius is your h value, your hypotenuse each time. So that's why we look at it as y over r is the definition of sine, and it all goes back to that right triangle and those side lengths found by Pythagorean theorem using those values. So this is a very important picture to keep in your mind as we go through here. And again, we're able to find the heights then each time above the ground, because if this is 1 and we have a theta measure each time, we can use sine to help us find this height of our pedal each time above the ground, and using that idea of opposite over hypotenuse. Now, when we're looking at the sine graph, when they're talking to us about the graph of this and comparing it on the calculator to the pictures here, the period and the amplitude of this, the amplitude is going to be 1, right? Because our midline is at y equals 0. And then the amplitude here, it's 1 unit above and 1 unit below that midline, or half of the total distance of 2, you would have an amplitude of 1 unit. And then if we're talking about this in radians mode, right, it repeated itself by the time it got back to 2 pi. So that is then the amplitude of this is 2 pi. Now again, we talk about sine, it's oftentimes we think about it in reference to that first quadrant, right, where it's x comma y and r here. So we usually tend to think about this in terms of the positive triangle aspect of it. But remember, if you're in another quadrant, just like we were talking about before, you want to think about where am I at and how that's going to dictate what your x values and y values are coordinate wise. But it always relates back to that quadrant 1 triangle, if you will. Everything else is in reference to that. Okay. All right, that's basically all I have for you now with lesson 15.3. It's just relating back our problems to the actual trig functions versus this real life situation. And we'll work more with sine, cosine, and tangent in activity 16. Thanks, everyone.